All right, so what we're looking at today is page of your notes says celestial objects. All right, so in astronomy, what we study are things that are outside the Earth's atmosphere. So like stars and planets and galaxies, things like that. Those things that are outside our atmosphere are what are referred to as celestial objects. All right. Something like a cloud would not be considered a celestial object because a cloud is within our atmosphere. All right. So anyways, a funny thing happens though when we start studying things in especially the nighttime sky, like stars. Now I'm going to take a step aside from this for a minute and explain how we see three dimensions. All right. We'll come back to this in a second. How you see three dimensions is your right eye is looking at an object from one angle, your left eye is looking at an object from another angle, and the image you see with your right eye and the image you see with your left eye are slightly different images. And what your brain does is takes the image from your right eye and the image with your left eye, and it figures out how far away that object is. That's how you get depth perception. When you have two different images, one with your right eye and one with your left eye that are different, your brain takes those two together and then figures out how far away that object is. That's depth perception. Now, if you had some crazy accident and you lost one of your eyes, you could still read and stuff like that, but you lose your depth perception. It becomes a lot harder to hit something like a baseball or shoot a basketball because you have a harder time figuring out how far away things are. Another thing with the depth perception, though, is when you're looking at objects that are really, really far away, the image you see with your right eye and the image you see with your left eye, the farther that object is away, the more close those two images become. And if those two images are too much alike, then your brain has a hard time figuring out how far away that object is. And that's what happens when you're looking at stars. I mean, one star you look at, you might see might be 1,000 times closer than the star right next to it. But you really can't tell which one's closer and which one's farther away. I mean, one of them might be brighter than the other one, but just because it's bright doesn't mean it's close by. There could be a dim star that's near and a bright star that's really far. So when you look at things like stars, your brain has a hard time figuring out how far away they are because the image you see with your right eye and the image you see with your left eye are very close. And what your brain does then is it just kind of gives them all the same distance. So all the stars, even though their distances are very, very different, they all appear as if they're the same distance. And that's what people initially thought, is that all these stars were the same distance away. And the only way they could come up with an explanation for that is that there must be this shell, like this crystal shell surrounding the Earth that had all the stars as points of light on it. And they call that shell surrounding the Earth the celestial sphere. So what a celestial sphere looks like is like this, where all those little points on it were the stars, and they're in this shell, this like crystal ball thing that surround the Earth. And like how the stars moved is that the stars would rotate like this around the Earth, and that's why they saw the stars moving during the course of the night. All right, so this is what people thought a couple thousand years ago. Now, obviously, we know this is not the case, all right, today. However, we still use a celestial sphere when we want to describe the locations of things in the sky, because it's a convenient method of describing locations in the sky. Now, this is how it would appear on the big picture. To an observer on the ground, it would kind of appear like you're a little guy inside of a glass dome. All right, so that's what this represents right there. This is like the celestial sphere is going to act like a dome surrounding you, kind of like a planetarium, and that the stars and stuff are locations on this dome. Again, we know that's not the case, but it's a convenient model used to describe the locations of things. Now, let's say I want to describe the location of something on that dome right there. How I go about doing that is by using two angles. We use something called the azimuth and something called the altitude. Now the azimuth just basically describes what direction the object is in the sky. So 0 degrees would be north. If it was east, it'd be 90 degrees. If it was south, it'd be 180 degrees. If it was west, it'd be 270 degrees, and so forth. So this tells me what direction it is on the horizon. The next number you need is the altitude, and that tells me how high that object is above the horizon. So if it points directly above me, that'd be a 90-degree altitude. If it's right in the horizon, it'd be 0 degrees. You know, something like that might be like a 45-degree altitude. So if I said that, like, if I was trying to describe the location of a star and I said that the azimuth, it had an azimuth of 25 degrees and an altitude of 40 degrees, what I would do is azimuth 25, altitude 40, that'd point to a particular spot in the sky. Or if the azimuth was 115, altitude 30, that'd be azimuth 150, altitude 30, that'd point to a spot right there in the sky. All right, so that's how you describe locations of things in the sky, is with azimuth and altitudes. Now that you have this knowledge of how to describe things, let's say you went outside at 9 o'clock at night and you wanted to describe the location of the Big Dipper. So you go outside at 9 o'clock, you find the Big Dipper, and you're like, you write down the azimuth, you write down the altitude. And then you go back inside, and then you go to bed, and then you're lying in bed thinking to yourself, wow, that Big Dipper was awesome. I want to go see that Big Dipper again. And you're lying in bed for a while, and it becomes like 2 o'clock in the morning, and you're like, I can't stand it anymore. I got to go out there to see the Big Dipper. Well, I got the azimuth and altitude written down. I know exactly where to look. So you go outside, like the azimuth, altitude, and you look for the Big Dipper. It's not going to be there. All right? And the reason being is during the course of the night, the stars move. The stars don't stay in one spot during the course of the night. With one exception, the only star that stays in the same spot is Polaris, the North Star. All the other stars appear to rotate around Polaris at 15 degrees per hour. So Polaris stays in the same spot, but the other stars move around at 15 degrees per hour. Now 15 degrees per hour should sound familiar to you because that's a number that we talked about before. What moves 15 degrees per hour is the Earth. The Earth rotates 15 degrees per hour. Because what's actually happening is the stars aren't moving. Stars are basically staying in the same spot, but the Earth is rotating 15 degrees per hour, and that makes them look like it's moving. So like right now, there's a bunch of little dots on the ceiling. I'm looking up at them and there's in one spot. Now if I start spinning around like this, then those little spots look like they're moving, but they're not moving, I'm moving. It just looks like they're moving. That's basically what happens with the stars. All right. Now, how they move, I'll show you over here. All right, so let's say that's the nighttime sky. Let's say here's the nighttime sky right there. Those are all a bunch of stars. And there's the Big Dipper right there. All right. Now remember how I said you find the Polaris is you find the Big Dipper, then you take the last two stars in the Big Dipper and you point up to it, and then it'll point to Polaris. So Polaris will be like up there someplace. Now, we said that all the stars move during the course of the night, except for Polaris. Well, if all these stars are moving except for that one, how do these two stars still keep pointing to that? Well, how they move is like this. the stars are moving like that. So all the stars are rotating around Polaris right there. And if you notice, these last two stars in the Big Dipper still point towards Polaris. Even though they're moving around, they're still lined up in a way where they point to Polaris. So because this is caused by the Earth rotating, it would take 24 hours to go all the way around once. All right, so that's how the stars move during the course of the night around Polaris. Now, again, it takes a long time to observe that, though. Now, sometimes people may take a video. They might put a video camera on Polaris, like a wide-angle lens or something, and take a picture of the sky in the video, and then you could time-lapse it and see how the stars move during the course of the night. Another way you could do it, though, is you could actually do it with a regular camera. Now, how a camera works. How a camera works, basically. All right, so let's say my shirt here is film. Cameras have this thing called a shutter. So you press the button on the camera, the shutter opens and closes. So what's happening in that split second when the shutter's open, the image, whatever you're looking at, gets projected on the film, and then it kind of gets sealed in there, and then you develop the film and you get a picture of whatever you're looking at, right? But you only get a picture of what happened during that split second, right? Now, some types of cameras, if you have a better camera, what you can do is you can leave the shutter open for a longer amount of time. So instead of just like that, you might have it open for like that, or maybe even a longer amount of time like that. The reason why you'd want to do that is if you're trying to take the picture of something under low light conditions, like you can't normally just like point a camera up at a star and go click and take a picture of a star. You won't get anything because the star is not giving off that much light. So you'd have to leave the shutter open on the camera for a while to give that little trickle of light enough time to leave an impression on the film. All right, so in low light conditions, you might want to have the shutter open on the camera for a longer amount of time. Or let's say I had one of these cameras where I could leave the shutter open for a longer amount of time. Let's say I left it open for a minute. And looking out the window right here, we got the Burned Area gas station across the street. So let's say I left the shutter open on my camera and I was taking a picture of the gas station. Now, I left the shutter open for a minute. All right, shutter closes, I get the picture developed. What I would see is the gas station would look like the gas station, the tree would look like the tree, the flagpole would look like the flagpole, but I'd also see some streaks across my camera, or across my picture. And what the streaks are things that were moving. So things that are moving are gonna leave streaks along one of these types of pictures, these long exposure pictures. Okay. Now, let's say I take one of these cameras that I was able to leave the shutter open for a long time, and I brought this camera to the North Pole, and I pointed this camera straight up to pointing at Polaris, because it's North Pole, Polaris is directly above. And I left the shutter open for a long time. Then I got the picture developed. Now the stars are going to move kind of like they did right there. Well, what my picture would look like when I got it developed like this. All right? So these are star trails. All right? There's Polaris, there's the point right there, and this shows you how much the stars move during the course of the time that the shutter was open on the camera. Now, at first glance, you may say these look like a bunch of circles going around Polaris, but if you look at them in closer detail, none of these are a complete circle. All right? To get a complete circle, the shutter would have to be open for 24 hours. None of these are a complete circle. It's a bunch of fragments of circles, but all together, they kind of look like full circles. But if you look at some of the more darker ones, like that guy right there, or this guy right there, I could actually make an inference about how long the shutter on the camera was open. Because it would take 24 hours to go all the way around. If I look, that's only about a quarter of the way around, and then this one's only about a quarter of the way around, and this one's only about a quarter of the way around. So that means that the Earth only rotated, about a quarter of the way around, which a quarter of 24 hours would be 6 hours. So these are how the stars moved over the course of around 6 hours. So these are called star trails. Now, this is a picture that I got out of a book. I also have one that this picture right here, way back when in 1996, I believe, there was a very bright comet called Hale-Bopp. And Hale-Bopp was a very bright comet, and it was in the sky for a number of nights. And my uncle wanted to get a picture of the comet, and he had one of these cameras where you could leave the shutter open for a while. But again, even though the comet was bright, to get a picture of it, you have to leave the shutter open for a while. So you can see a nice picture of the comet right there, and there's the comet's tail and so forth. But what you also can tell by looking at that picture is how much the stars moved during the time that he had the shutter open. So you don't see stars as little points of light, rather they're little like dashes of light, because he had the shutter on the camera open for a few minutes. Now, another thing I can notice about this picture is Polaris doesn't move. So Polaris would be a fixed point. And I don't see any fixed points in that picture. So that's telling me that Polaris is not in that picture. But what I can do is figure out where Polaris is located relative to that picture. If I notice all these little dashes, they're all kind of bending around like this. So whatever they're rotating around is going to be something that's located down here. So relative to this picture, Polaris would be down here someplace because their movements are kind of bent like that. All right. But anyway, so that is celestial objects in the celestial sphere and how the stars move during the course of the night.